So today we're going to look at how to look at your electron configuration and determine if it is a ground state electron configuration, an excited state electron configuration, or an impossible state electron configuration. So let's first define these three situations. If you have ground state electron configuration, that's the electron configuration just like you would normally write it. It represents the electrons when they're in their lowest, most stable energy state. Don't forget that chromium and copper, the two exceptions that we learned about, those are the ground states for those two elements. So like chromium and copper will look a little different. They will have a 4s1 3d5 for chromium and 4s1 3d10 for copper. Now the excited state electron configuration will look a little funny when you look at the end of it. The electrons, what happens is if you add energy or electricity to an atom or to a compound, the electrons can get excited and they'll actually jump to a higher energy level. They could fall to a lower energy level, giving off light as well. But the excited electron configuration is going to look a little strange at when you look at the superscripts. The superscripts typically will be lower than the maximum value, and then the electron configuration would have continued on as if it had filled up the orbital, like alpha tells us we're supposed to. Now, the impossible state electron configuration just simply cannot happen. These will be things that will be totally breaking every rule that we have learned in this chapter. Oftentimes, you can recognize it because the superscripts in your orbitals will be much larger than the maximum allowed value, or you will find orbitals in energy levels that they're not allowed in. For example, you could not have an F orbital in the first energy level. So if you were to see a 1F14, that would be impossible because you can't have the F orbitals. They don't come in until the fourth energy level. Likewise, you could not have like a 2p7 because the p orbital cannot hold more than 6 electrons. That's it. So the impossible ones should kind of stick out like a sore thumb, really. So let's look at some electron configurations and determine if they are ground state, excited state, or impossible state. What I would do first of all is figure out who the electron configuration is representing. So if you add up your superscripts here, you see we have 3 electrons. So what that means, if you look at your periodic table, that means this is the electron configuration for lithium. So what you want to do is look at lithium and say, ask yourself, is that how I would normally write lithium's electron configuration? Would I say 1s2, 2s1? And you sure would. That's exactly how you write lithium's electron configuration. And this means this is its ground state. That's in its lowest energy state. Let's look at the second example. 1s2, 2s2, 2p5, 3s1. So let's add up our superscripts. 2 plus 2 is 4, plus 5 is 9, plus 1 is 10. So there are 10 electrons in this electron configuration. And if you look at your periodic table, that means that this electron configuration is representing, or supposed to represent, neon's electron configuration, because it's the element that has 10 electrons. But we normally would not write neon's electron configuration this way. Notice here, the 2p orbital did not get filled up before we moved to the 3s. What happened was one of the electrons was excited and jumped up to the 3s orbital early. So this is what we call the excited state. The reason it's not impossible is because it is possible to have a 2p5 position. There is an element on the table that's a 2p5, and there's a 3s1. Those are allowable orbitals in energy states. But that's not normally how we would write it. Notice here that the superscript is lower than it should be before we moved up. So this is the excited state. Let's look at number 3. 1s2, 2s3, 2p1. Now look at this, 2s3. Can you ever have 3 electrons in any s orbital? And the answer is no. That will never, ever, ever happen. An s can only hold 2. So impossible electron configuration. Cannot ever have that. All right, let's look at number 4. Add up your superscripts. 5 plus 1 is 6. Plus 6 is 12. 13, 14, 15, 16. This is 16 electrons we have here in this electron configuration, which means this electron configuration is sulfur. Use your periodic table to make sure you can agree with that answer so far. Sulfur is who we're looking at. And 1s2, 2s2, 2p6, 3s1, 3p5. Everything looks really good until you get right here. Because what should we do before we move to the 3p's? We should say 3s2. Notice it jumped up too soon. So this one is an excited state. The reason, again, it's not impossible is because it is possible to have a 3s electron or 3s orbital with 1 electron in it. That is possible. It is possible to have a 3p electron with 5 electrons in it. So it's just excited. One of the electrons jumped up too early. Okay? Let's look at the last one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Now, if you add up the electrons here, 5 plus 1 is 6, plus 6 is 12, 13, 14, plus 6 is going to be 30. Sorry, let me recount that. 5 plus 1 is 6, plus 6 is 12, 13, 14, plus 6 is 20, 21, 22, 23, 24. 24 electrons here. That's what happens when you get in a hurry, y'all. All right, so there's 24 electrons here. So this is chromium. Now, is there something special we're supposed to remember about chromium? Maybe chromium and copper? That's right. They're the two exceptions to the electron configuration. Because this electron configuration, when you get to the end, like right here, it looks kind of strange. You would normally think you'd say 4s2 before you say 3d anything. But remember, the half-filled s orbital is very stable, and so one electron got promoted early to make the d orbital half-full. So this is how chromium gets its most stable electron configuration. This is actually chromium's ground state. Chromium and copper's ground states will look excited, but you just have to be on the lookout for them. That's why I always encourage y'all to make sure you add up your superscripts first and figure out who it is. So if it's ever chromium and copper, take a second to look at it and see if that is the way we learn to write their electron configurations. Okay, thanks a lot. I'll see y'all tomorrow. Study hard for your test.